Hi, thanks for Mies. So the work that I'm going to present is with Rotem Arnon Friedman and Zvika Bakersky, and we're all at the Weizmann Institute. And I want to thank Rotem for allowing me to borrow some of the graphics that you'll see in the slides. So you should think of the work that I'm going to present as being rather exploratory. So we give a few definitions that we believe are important. We state some important, some useful properties of them and kind of hint at some applications. But there is much more that we believe can be done and hopefully will be done. So this is a good work for open questions. I'll try to state some. So because there's a bit of a shift of topics compared to the previous talk, let's kind of warm up by reminding ourselves what is entanglement theory, even though obviously we've heard a lot about it during QIP. So loosely speaking, the goals of entanglement theory are to introduce quantitative measures of entanglement such that the study of these measures allow us to characterize some properties of entanglement. So there's a few very basic axioms that we generally expect any such measure to satisfy. For example, we generally require that the measure should be non-increasing under LOCC. So LOCC stands for local operations and classical communication. So it looks like that. So given the basic axioms, there's a whole range of measures that satisfy them. And each of these measures is interesting for a different reason. For example, the measure might have an additional property, such as some form of monogamy, or maybe this measure happens to characterize the ability of the entangled state to support or achieve a certain operational task, etc. So kind of jumping ahead a little bit, the main message of the talk is that we need more measures. So I'm going to try to argue that there are some important phenomena that are not captured. Okay, by any of these measures, and so I'll describe this. To get there, let me introduce just two very basic measures that will play a role in the talk. First of all, there's the von Neumann entropy. So the von Neumann entropy is simply the entropy of the reduced density matrix of a subsystem. So it's a very good measure of entanglement for bipartite pure states. It's just the entropy of the vector of Schmidt coefficients. However, it's pretty much irrelevant for density matrices because it only talks about the reduced density of one system. So as a measure of correlation, it's useless. It doesn't make a difference between correlations between A and B or A and C or A and the entire world. So it's the first measure. The second measure is distillable entanglement. So informally, the distillable entanglement is the largest number of EPR pairs that can be created by acting on the entangled state using local operations and classical communication up to some target fidelity. So in pictures, it looks like this. I want to emphasize that, so here for the talk, I'm going to talk about one-shot distillable entanglement. What one-shot refers to is the fact that you have a single copy of your density matrix given as input. So beware that this does not mean a tensor product state. There's many qubits just because it's a many qubit state, okay, but it's a single globally entangled state across A and B. And using local operations and classical communication, I attempt to distill EPR pairs from it. If you like formulas, this is the very classic formula for the distillable entanglement, but it's not too important to be able to parse that for the talk. Okay, so we have these two measures. Let's practice on a couple examples. So I chose two bipartite states for you. The first one is very simple. It's just n EPR pairs across A and B. And the second one is a Haar random state. A Haar random state is just a uniformly random state of 2n qubits. So for the EPR pairs, the measures are very straightforward to compute. The Schmidt rank is 2 to the n, the von Neumann entropy is n, the distillable entanglement is n. For a random state, it's a little bit harder, but using fairly standard concentration measure arguments, you can show that these measures are near maximal for a uniformly random state, which is pretty intuitive. So for the Schmidt rank, you get 2 to the n up to a constant, and the von Neumann entropy and the distillable entanglement are also maximal up to a constant. This is called Page's theorem, I believe. So then you can ask, well, okay, so we observe that these two states are not really distinguished by these entanglement measures or by any entanglement measure for the matter. So is this okay or not? On the one hand, you could say, well, sure. I mean, of course, they have the same entanglement, look like a uniformly random state up to a local unitary on one of the systems to align the Schmidt bases. This basically looks like any PR pair, so of course they have the same entanglement. On the other hand, you could push a little bit and say, wait, so what's the unitary rotation that you should be applying exactly, and how do you apply it? So this is where computational entanglement theory comes in. Essentially, we're going to introduce a computational measure of distillable entanglement, and we'll be able to evaluate that measure on any PR pairs and get n. And we'll also be able to evaluate it on a hard random state and get essentially 0. Intuitively, the reason for that is that even though information theoretically both states contain the same amount of entanglement, in the hard random state, this entanglement is not computationally accessible. So I'll return to that example in a bit. It's a good time to summarize the main results that are in the paper. So first of all, we introduce computational measures, not only the distillable entanglement, but also for the entanglement cost. And the main argument that we have in favor of the use of these measures is that we believe that they should be the relevant measures whenever you're interested in quantifying entanglement in a scenario where computational efficiency is important. For example, you're designing protocols for the quantum internet, and for this you need to be able to distill entanglement at a certain rate to perform teleportation. It's important that you measure the distillable entanglement of the states that you can prepare, taking computational considerations in account as if you want an efficient protocol for your internet. So that's the first contribution. We also show separations between the measures that we introduce and the traditional measures. I just already showed you a separation in the previous slide. There's some other ones. And then the second contribution is that we introduce a notion of pseudo-entanglement that mirrors previously existing notion, but is adapted to our definitions. And we argue that this notion makes a step in the direction of trying to make statements about the ADS-CFT correspondence. I'll get to these two items in the second part of the talk. First of all, I want to give you a definition and then state some separations. So these are the first two items, and I'll get to 3 and 4 after that. So we want to define computational entanglement measures. For this, we need to fix a computational model. So we use the standard model of polynomial size. Oops, sorry, I'm not there. Sometimes this doesn't. Okay, we use the standard model of computational size circuits. So basically, the main change that we make is that instead of considering general LOCC, we require the local operations to be implementable by polynomial size quantum circuits and the communication to be polynomial in size. Because the notion of polynomial time computation or efficiency only makes sense in a asymptotic sense as a function of some size parameter, we need to talk about families of states now, not a single state. So the measures that we introduce will not measure the entanglement of one state at a time, but instead they'll measure the entanglement asymptotically of a family that depends on the parameter lambda. So this lambda is a size parameter. You can think of it as the number of qubits of the state if you want, but it doesn't need to be the number of qubits of the state. It's just some indexing parameter. Okay, and once you've fixed the computational model, it's straightforward to define distillable entanglement. So this will just be the largest number of EPR pairs that you can distill efficiently from your state asymptotically. Actually, if you want to make the definition precise, you have to be a little bit careful in what order you fix the parameters. So slightly more precisely, we say that the function m of the parameter lambda is a lower bound on the computational distillable entanglement if there exists a polynomial P and a family of LOCC maps that can be implemented in that polynomial size, such that for every lambda, the corresponding map can distill m of lambda EPR pairs from the corresponding state. All right. Okay, so let's talk about separations now. So we already saw one. Using a fairly straightforward counting argument, you can show that for a uniformly random state, the distillable entanglement is n. This is previously known. whereas you cannot distill any meaningful number of EPR pairs from it, as the size of the state goes to infinity. You can complain a little bit about this separation, because you can say, look, I mean, okay, this is pretty obvious, right? You're taking a state that's not even efficiently preparable, hard random state. How can you expect to distill anything efficiently from it? Okay, so we push a little bit further, and we give another separation where the states are efficiently preparable. So for this, we need to start making computational assumptions. So we make the most standard computational assumption in cryptography, which is the existence of post-quantum or quantum secure one-way functions. And under that assumption, we can give a family of states that are efficient to prepare, have high distillable entanglement, but have, again, basically no computational distillable entanglement. If you know a little bit of crypto, if you've played with these things, it's really not hard to come up with such states. You basically take EPR pairs and apply a one-way function on one half of the system. So this is easy to do in the forward direction, but cannot be undone efficiently by the definition of a one-way function. I'm not going over computational entanglement cost in the talk, but let me still mention that we have also separations there. I want to mention it because the separations are a bit weaker. We need to assume a stronger computational model, which is the random oracle model. And also, in fact, the separation only applies for the one-way entanglement cost. Intuitively, the reason that it's harder to prove separations here is that the tension between the state being efficiently preparable, but not efficiently preparable locally, is a little bit of a subtle tension. And I believe that this can be improved. And so if, for people who are interested in like tight results and things like that, there's definitely some work to be done there. All right, so that's all for the separations. Now let me move to the notion of pseudo-entanglement. So at a high level, what's pseudo-entanglement? So first you need to define a maximal or an ideal resource. So for us, this is the notion of a computationally maximally entangled state. So this is a state that has maximal entanglement, but furthermore, this entanglement is accessible, so you can efficiently distill a maximal number of EPR pairs from it. That's the maximal resource. And then you take kind of a dud, so in this case, the state is pseudo-entanglement if it can be prepared using a very small number, efficiently using a very small number of EPR pairs, yet that state is computationally indistinguishable from your maximal resource, from which a very high number of EPR pairs can be distilled. So of course, I'm kind of sweeping this under the rug, but to define these things precisely, you need a notion of a key that's used to specify the states. And when I say computationally indistinguishable, I mean without access to the key. Otherwise, this would be impossible to achieve. So the notion of pseudo-entanglement, not this particular notion, but the notion in general, this was introduced in previous work of Aronson. And there was a talk about this on work by Boulon et al. I think the talk was by Tony Medgar, I'm not sure, on Tuesday. So they give a construction of pseudo-entangled states according to their definition. So I'm just flashing the definition on the screen for you to make the difference with the new notion. So this is the kind of computational indistinguishability that they show. And this family is pseudo-entangled. Why? Because on the one hand, if this S here, this S is a subset of all 2 to the n bit strings. If it's sufficiently small, then you can show that this state has low entanglement entropy if you cut in the middle, or in fact, if you cut anywhere. Yet it's indistinguishable from a hard random state, which, as we saw, has high von Neumann entanglement entropy. This construction is not satisfying with respect to our notion for 2 reasons. First of all, even though this state has low entanglement, von Neumann entanglement entropy, it's completely unclear how you could prepare the state using a small number of EPR pairs, as small as its entanglement entropy, locally. You can prepare it efficiently if you have access to the whole system, but if you're trying to do it using LOCC, it's not clear that you can do that. And second of all, the hard random state has high entanglement entropy, but from the point of view of like using it in any kind of application, this entropy is completely inaccessible. So it's not clear from our point of view how interesting it is to be indistinguishable from a random state. There's not that much you can do with a random state. So we give a different construction. The construction is very much inspired by previous works. It's relatively simple. It's actually the same as the one with the one-way function that I gave you earlier, except that we give a whole family of constructions that's tunable. So instead of having a one-to-one one-way function here, we take a many-to-one one-way function. And so the more compressible it is, the lower the entanglement will be in the state. Yet all these are computationally indistinguishable. So if you take non-compressing, so just a one-to-one one-way function, then you get a permutation that's invertible, efficiently invertible. Then you have a computationally maximally entangled state. If you take the compression factor down all the way to super logarithmic, then you have states that have much lower efficient entanglement cost. Yet all this range here we show is computationally indistinguishable. So they're pseudo-entanglement. Okay, so now to conclude the talk, let me briefly and quite superficially go over one of the motivations that we had, which is to explore further the initial motivation for pseudo-entanglement, which dates back to work by Boulan from, I think, 2017 or 19, which is to study the computational efficiency of the ADS-CFT correspondence and try to make statements about that. So let me recall the main parameters of this. So ADS-CFT is a duality between two physical theories. First of all, you have ADS. ADS stands for anti-de Sitter space. This is a theory of gravity in two spatial dimensions and one time dimension. We generally represent it as the inside of this cylinder here. And CFT is a quantum field theory, a two-dimensional field theory that is imagined to live on the two-dimensional boundary of the cylinder. So here, this is just a cut, a two-dimensional cut of the cylinder. And for simplicity, I'm going to use the cut in the following pictures. What's interesting, or one of the interesting aspects of this duality is that it relates physical quantities in one theory to physical quantities in the other. So that's computationally interesting, conceptually interesting, but it can also be interesting from a computational point of view. And the reason is that some calculations, some of the quantities can be easier to compute in one theory and the other. And this is used in practice to do calculations in ADS. You do them in the CFT instead, and then you translate them back. And there's some kind of a dictionary for that. The question that was asked in this earlier work I already mentioned is what is the computational efficiency of the dictionary? If you want to use it to leverage easy calculations in one theory to the other, you need it to be computationally efficient. And they proposed to probe that question using the notion or actually Aronson, I think, proposed to probe that question using the notion of pseudo-entanglement. So let's do a little bit of a thought experiment. Let's use the dictionary. So we create a quantum state in the field theory here on the boundary that has small entanglement. The dictionary and actually a specific formula there, the Ryu-Takiyanagi formula, corresponds small entanglement to a certain, loosely speaking, geometry inside the ADS, the gravity theory. And if you have a high entanglement, this will correspond to a different geometry. These geometries are such that in the ADS, they're easy to distinguish. However, if you believe in pseudo-entanglement says that there are entangled states that have low entanglement that are computationally hard to distinguish from high entanglement. And so if you have this, then it means that at least in some instances, this dictionary must be hard to compute. So that's the idea, but there's a lot of asterisks, there's lots of caveats and subtleties, and the goal of our work is just to remove some of the asterisks. So what are some of the main asterisks? One of them is you have to be careful about what kind of entangled states you're talking about. And in particular, this correspondence corresponds entanglement to different geometries, entanglement between different subregions of the CFT, not a region in its complement. So once you're talking about different subregions, you need to talk about mixed states, not only pure states. Now, that's one item. Second item is that it's not clear at all that the von Neumann entropy is the right measure of entanglement. In fact, there's a bunch of recent works by Ackers and co-authors that point to more subtle measures of entanglement that happen to be very related to the distillable entanglement to be the right measures to which the correspondence applies. And lastly, why computational assumptions? So there's interesting. I think we're going to hear about this maybe this afternoon from Alex May. There's a nice idea that tries to leverage the correspondence to show the existence of certain kinds of non-local computation protocols on the boundary in the CFT, to derive this from arguments that are easier to make in the bulk. But in order to leverage this, you need the correspondence to be computationally efficient. All right, so because our measures apply to density matrices in general, because they take computational efficiency into account, because they look at distillable entanglement, we believe that they're at least towards the right measures in order to further explore this correspondence that has received a lot of attention. There's still some asterisks, and it's not like the examples that I gave you actually exist in this CFT, or can be given any meaning according to the correspondence. Obviously, there's more work that should be done there, and we're just making steps in that direction. All right, so let me conclude. So the main contribution that we have is to introduce some definitions that try to capture entanglement in a computational setting, whereas whether this entanglement is computationally easy to create, or it's computationally easy or at least feasible to distill EPR pairs from it. And there's many things that remain to be done. Let me just give you a couple suggestions. I mean, first of all, obviously, is to extend the theory. Of course, you can study other measures, and you maybe try to find other applications for it. One kind of toy question is that when I discussed pseudo-entanglement, the work that was discussed on Tuesday, they study entanglement across all cuts. And I'm wondering if this can also be achieved in our setting. Another kind of question is about monogamy that I mentioned earlier. So what are properties? Does computational entanglement exhibit monogamy? Yes, no, sometimes. Can we study that a little bit? Maybe some other interesting properties that other measures capture, and what about them in the computational setting? So there's a whole lot of open questions that could be studied there. And let me end here. Thank you.
Thank you, Thomas, for this nice talk. We have time for some questions.
Thank you for the nice talk. So I have 3 questions. So first question is, so you constructed pseudo-entanglement from one-way function. Can you construct from some weak assumption, like EFI? Or
that's a good question. I forgot to mention it, but actually we can. So we do construct it from EFI.
Oh, from EFI.
Yeah.
Okay. So second question is there any computational assumption necessary for the existence of pseudo-entanglement?
Probably because the states need to be efficiently preparable. So if you want it to be hard to distill from them, I think so. Yeah.
But you don't know which assumption is this?
No. We don't study, right. So you could also study pseudo entanglement by itself as an assumption and try to relate it, in the converse. And that's a good question. We don't do that.
Okay. So third question is there any crypto application?
Yeah, so I wish I could answer that, and there's obviously cryptographers among my co-authors, but I don't know.
Okay. Thank you.
Thank you for the nice talk. I wanted to ask about a certain property of entanglement measures, at least of some of the entanglement measures, that entanglement can be reduced if the system goes through a noisy channel. Let's say you have a one-sided noisy channel or two-sided noisy channels. And then, at least for one-sided noisy channels, certain entanglement measures allow a kind of factorization of so the final entanglement is given by a quantity that characterizes the state, the channel, times the initial entanglement. Is that something that you have looked at with your entanglement measure?
It's a good question, actually. This showed up yesterday at some point. No, we haven't looked at that. I guess it's a good question. We can talk about it after.
Yeah. Can I ask one more, small one?
Sure, maybe a quick
Thank you. Concerning your what was it called? the entanglement, not the bound entanglement, but the other one that you had, the
Cost or
pseudo
just
pseudo
delivered?
entanglement.
Pseudo-entanglement.
The pseudo entanglement, does it have similar properties as the bound entanglement, that if a state is entangled and its partial transpose is non-negative, then we know it's bound entangled? Is there something similar too for your pseudo entanglement? I didn't really understand the physics of pseudo entanglement. Maybe you can shortly say something.
I'm not sure notions are related. So these states are not bound entangled in general. I think it's conceptually it's a different notion compared to bound entanglement. Because you really have two different families of states, and a family has high entanglement, a family has low entanglement. When it has low entanglement, it has low, you could do it with the von Neumann entropy, so it could have low, just low entropy, high entropy. What's important about it is that the two families are computationally indistinguishable. So it means that an efficient procedure, but partial transpose is not physical. So an efficient physical procedure would not be able to see that this state has low entanglement, because if it could, it would distinguish it from the high entanglement.
Great. So one question over here.
Hello, hi. You mentioned some of the entanglement measures in the initial slides. So is it known that, let's say for bipartite entangled state, how one measure is related to the other?
Yeah. There's many relations between these measures. If the states are pure, they're virtually all collapse to the same thing. If the states are mixed, no, there's a whole range, but there's many relations. There's definitely inequalities, and there's a sense of when these inequalities are tight. And
okay, okay, thank you.
So any other questions? We have time for. There's one over there.
I was just wondering if you could see any connections with these computational measures with topological phases or quantum error correcting codes based on these kind of things like toric code, etc.
No, I'm happy to talk about it. I don't see a connection with the toric code. No, it's even hard to see what you have in mind, but maybe we can talk about it later so that you can explain.
Sure.
Any other questions? We have time for one more.
Hi. Thanks for the talk. I see your approach as kind of you introduce a local resource, which is a local classical computational power locally, and you put it together with with a global resource entanglement, and So you could also do something, or I was thinking what happens if you say, okay, my local computational power is bounded, so I can only use polynomial local algorithms, but entanglement is given for free. So have you thought about this, or do you? Yeah.
So if you're okay, I guess it depends what task. I think this is actually, I'm not sure if this is the framework of local computation. So you can definitely study what kind of algorithms can be or transformations can be implemented in this case. And for us, it was interesting to study when the entanglement is restricted. The starting point was entanglement more than polynomial efficiency, and we're adding this. Yeah.
Right. I mean, and you put entanglement and computational efficiency on the same kind of footing, and but
no, not really, because entanglement, we're interested in quantifying it relatively finely. So we have a whole range of parameters. This entanglement could be a constant, could be logarithmic, could be polynomial. Whereas for the computational efficiency, we just say it's polynomial time, and we don't look at it more finely. So I think entanglement is the more important thing we're trying to characterize, and then there's a general framework around it of polynomial time that we're not interested in refining any further.
Okay. Yeah. Thanks.
Okay, great. So it's time for the coffee break. Let's thank Thomas for the nice talk and both speakers this morning.